Welcome. My name is Nick Lotz. I am with Voxel 51, and welcome to today's webinar. So the kind of, you know, what I might call, I'm not quite provocative title, but title all the same is called What's Hiding Behind Your F1 Score? How to Uncover Hidden Model Failures. So really the goal of today's webinar is discussing and understanding what causes models to fail and why, largely within a computer vision context. So a little bit about me. My name is Nick Lotz. I work here at Voxel 51. Our goal as a company is to help you maximize the ability of your AI data to train and deploy better models. A common sort of theme that I will be focusing on throughout this talk is the concept of data-centric AI. That is, there's been so much advancement in, for lack of a better word, the math behind AI models over the past couple decades in particular, where we're often starting to realize that moving the needle on model performance is due in large part to your data sets versus necessarily tweaks to the model architecture itself. So that's going to be a very large focus of today's call. My background is in kind of the originally in the process engineering space. I've been a software, machine learning, and DevOps engineer by trade for quite a while now. I am based in the southeastern US in Nashville, Tennessee. And my life goal when I am not kind of hacking around on the computer is to do the exact opposite of that. Or I should say, when I'm not hacking around the computer at work, I try to disconnect and hike around as often as I can. One of my main life goals is to see how many national parks in the US I can visit, and I've recently expanded my goal to see if it could be as many national parks in the northern and southern hemispheres that I can visit. So thank you for everyone who's joined so far. The way this is going to go is I will be kind of doing a combination of slides and demos in order to kind of present and walk you through basically how to uncover model failures. If as questions come up, feel free to use the Q&A portion of the call. You might need to find it by clicking like the little three dots in your Zoom client. But I'll be monitoring that as those come through, and then I'll be leaving time at the end as well to field any questions. So we have an hour. Here's where we're going. This is really for anyone who is interested in building better models. The focus is going to be on the causes of what cause models to fail, and largely from a data-centric perspective, and then moving the needle forward on pushing, better model performance through better data. So whether you're a machine learning engineer or QA engineer, whether you manage software projects or visual eye applications, anyone who's interested in shipping better models quickly with the visibility and control of what contributes to their model's performance in the first place. And that's a big thing because, to a large extent today, while there's certainly many techniques for evaluating model performance and the reason models perform the way they do, modern deep learning models are in many ways black boxes. And sometimes the insight you need as to why a model performs the way it does can really only be illustrated on the data side of things. So we're going to learn a few key things, why metrics can be misleading. So even if you have, good precision, good recall, which would be a good F1 score, what can be behind that can cause your models to fail in critical scenarios? A lot of that will then come down to edge case detection. If you've isolated what scenarios cause your models to fail, how can you get better insight into what those edge cases are, and how can you isolate those relevant cases in your data? A really nuanced and hidden mechanism that can cause models to fail are errors in the ground truth. That's a very those cause silent failures, and that can be a real pain to debug because those that wouldn't contribute necessarily to your model metrics that compare to ground truth, because if the ground truth is wrong, that'll throw everything off. But it will definitely contribute to how your models behave in the wild. So how can we kind of go through an iterative loop of ensuring that our label QA and our labels are as good as they can possibly be? Um, Alongside that, when we use the term edge cases, we're thinking of kind of the long tail of performance where there might be some very easy scenarios that the model, performs well in, but it's those rare scenarios that maybe aren't represented properly or maybe even overrepresented in our data set that we need to learn and debug. And the goal of all this is ultimately to get into a culture of continuous model improvement. I think, machine learning has appropriately taken lessons from the software industry over the past 10 years, where being able to ship fast and make incremental changes results in much better performance in the long run. A couple things that I'd like to direct you to for those who are on this call. One is a good resource is a blog we put out not too long ago that also has an accompanying white paper that can be reached here. Sorry, I don't have a QR code up here, but if you follow this link, it takes you to a blog that is kind of goes into a little bit more of the kind of I'd say written detail of what I'm going to kind of talk about and demo here. And there's also an accompanying white paper that goes with that article also. In addition, you can use FiftyOne in a few different ways, which is going to be the platform I use to go through these concepts. I'm going to be on a internal instance of FiftyOne that I can use with like pre-built data sets. We have a public instance called try.51 that you are welcome to explore. It includes some of the same data sets that I'll be showing here. In fact, the same data sets I'll be showing here. And you can kind of explore around that as well. So, with that being said, let's get started. And I want to lay a little bit of groundwork here is to why traditional model performance metrics can be misleading. And this is probably something you've learned before. If you are familiar with kind of the common model performance metrics, often, when you learn this in school, for example, and even in the real world, you'll learn that, okay, the F1 score is just a harmonic mean between precision and recall. The number of false positives and total positives and even the pooled F1 score can, can be misleading if there's like edge cases that your model fails catastrophically on. But just as a reminder of that, again, this kind of basic, I think, non-super colorful slide is just giving us a reminder of, ultimately the math under the hood, which is just algebra in this example, is going to just result in the metrics that we would get in whatever evaluation tool we use that might give us a first pass at whether a model is successful or not. So we have precision and recall, accuracy, specificity, and then again, F1 is just the harmonic mean between precision and recall. And in general, like these metrics can tell us a lot. They can give us a necessary minimum threshold, a floor of model performance, but they don't tell the full story. And let's take an example on why the math here might be misleading. So let's say that let's say you're in a manufacturing setting. So and you're performing anomaly detection over your products. And let's say we ultimately have like a pooled set of products, or we have a certain product an individual product that we're trying to determine our model's performance on when it comes to anomaly detection. And let's say that like conceptually we can divide our set into two groups. A group A we might call easy samples, like the relatively typical cases or very obvious anomalies. And let's say, just to use round numbers, we have 900 samples, and the ground truth tells us that maybe 805 of those are true non-defect samples, and 95 of those are true defects. So again, this is the ground truth right now. This is what we know to be true. And let's say we also know that we have a set of hard critical cases of 100 samples. These might be safety critical cases where the sorts of anomalies are not an option, or they might be nuanced and like hard to detect based off both the sensors that we have and due to the sensors we have, and also maybe some of the current, our models so far. And maybe out of those 100 samples, 95 of those are true and defect free, and 5% of those are like true positives in terms of having anomalies. Well, again, if you do the math, if you take the F1 score of group A, it might be very good. But if you and let's say we have a model and it performs very well on group A, and it performs close to catastrophically on group B. Again, F1 score is like relative. There isn't a magic number that tells you whether the model performs well or not, but just based off the model performance here, B is very bad. So it only detected true positives, 30 false positives, several false negatives, which can be especially bad, and then 55 true negatives. Well, the pooled F1 score, if you do the math, ends up being 0.84, which we might decide is pretty good. But in reality, the group B samples, which are our like critical cases that might have might be safety critical cases or just might be edge cases that we know we need to handle, the model still does not perform well on. Okay, so what do we do about this? This math tells us again that there is a core subclass of our data that the model fails on. The overall data set, success metrics in terms of model performance aren't telling us really the full story. Again, with this 0.84 value. So what this ultimately means in practice is we need to go back to our data sets. We need to go back and see what is it about this group B set of samples that cause our models to fail. And we might even need to go back further. The fact that I even have this data, that the model does not perform well among group B samples, I'm kind of taking for granted here, right? If we include like a pool set of samples or items in this case, how do I even get this spliced out information in the first place? Well, the way we can do that is through using a platform that allows us to have our data front and center and then perform basically end-to-end analysis of our data, including model evaluation metrics, scenario mining, and then also augmentation and balance of our data set through new samples, quality analysis of those samples, and so on and so forth. So the product that allows us to do this is FiftyOne. Again, if you haven't used FiftyOne before, has both an open source distribution and a enterprise edition. Some of the features I'm going to talk through are available in both features. There's a couple I point out that you won't see in open source FiftyOne if that's what you're using, and I'll be sure to point that out along the way. So let's look at an example here. So this example I'm showing on the right is the MVTex data set. So this is a common benchmark manufacturing data set that I'm going to pull up here in just a moment. And to the question in chat, how did he know in this case what was in group B? So I'm a little bit burying the lead here. So kind of like I said before, I'm kind of beginning with the end and the underlying knowledge that we know our F1 score is low, or not that we know that we've have issues, is that a certain class of data that I'm just calling group B, it so happens the model didn't perform well on. Now, as I said before, how did I like know that this group B set is a problem? Well, that will come to what we call scenario mining, which we'll get to in a moment. But ultimately, we know that out of these two sets, one of them we know are like hard critical cases. But again, we might not identify that until we actually dig into our model evaluation metrics. And we can see that there are certain qualities of our data that if we slice out that part of the data set, it suddenly shows us that the model is not performing as well as we should on that particular case. So it might be like certain lighting conditions in our manufacturing data set and so on and so forth. So again, I'm kind of burying the lead here. I'm beginning with the end just to show you that a total F1 score doesn't tell the whole story. And then we could use some tools to find which subclasses of data might um, result in failure in the wild that isn't fully accounted for by our overall performance metrics. So yeah. So let's take this data set, and I'm going to start with this just to kind of show you that the MVTech data set, which is taking a little while to load for some reason. I think it's because it's loading the segmentation masks here. Here in FiftyOne is the exact data set that I was showing here. And even before we look at model evaluation metrics, we're able to kind of filter, slice, dice our data set as needed. So for example, the MVTech benchmark data set has a whole bunch of categories of objects in it. So at minimum, I can filter by the type of object. So maybe we're looking at I don't know, toothbrushes, for example. And then in addition to it, the label fields can also be overlaid as well. So here we have a combination of classifications as well as from several different models that have been evaluated on this data, as well as anomaly segmentation masks. So for example, our PADEM model, we can see there's not a whole lot of examples here, but we can see here and there's little dots here that represent segmentation masks of where the model thinks there might be anomalies. There are also um, ground truth segmentation masks here as well. So at minimum, um, we have this ability to kind of slice and dice data. You can also sort by, you can also put confidence thresholds here. So for example, let me start with the PATEM one. Or even I can do the classifications here. So maybe I want to have a minimum confidence threshold of like 0.4, which it actually doesn't look like there's any here. Oop. The demo gods were not in my favor there. Let's go back here for a second. I might jump to a slightly different data set here if there's some slowness. Let me do this. Let me go to the model evaluation. So if we look at the model evaluation field, we can see that we have several different classes or several different evaluation runs through which we can look at critical metrics. So for example, we have PATEM for all different objects, and we have patch core and another anomaly detection model for a bunch of different objects as well. And at minimum, we can start to see our like core metrics here. So for example, if I click into the PATEM model, I can see that the accuracy, precision, recall scores here, they're effectively the same based off the fact that we don't have any false positives for this particular model against this particular class. And we can see the metrics for a single model, and we can also compare models side by side. So we can also look at the patch, so that's PATEM. We can look at the patch core model as well with respect to the same class, and we can see where it performs in terms of precision, recall, F1 score, which in this case, they're very, very close in this example with this toothbrush class. We can also look at confusion matrices. So we can see where the model confused false negatives and false positives. Let me do this here. So for example, for the PATEM model, where the model confused normal and defective samples, and we can root out false negatives and false positives. So here, if I click on one of these examples, we can see that, let me get this straight. Okay, yeah, we can see that well, this is just wrong. It's not a potted plant. I think that's another classification model that's not relevant here. We can see that the ground truth says this is an anomaly. The patch core model agrees it's an anomaly. So this is a false negative, right? And those can be especially with classification, it's not quite as big a deal. But with object detection, especially false negatives can be huge because you're effectively not detecting something that should be there, which the absence of that detection makes it a lot harder to root out possible false negatives because you can't find what isn't there is basically the issue. But you can start to see, wait, maybe what attributes is it about the samples that might cause these issues? Now, this is a pretty typical, uh, um, a pretty common benchmark data set that for the overall model evaluation metrics, we can get some insight, if the F1 score is good or bad, we can start to root into, what are the possible false positives, false negatives, what is held in common or not in common between different model runs. What it's still not telling us are those subsets alone. What this isn't telling us are those subsets of classes that I talked about earlier. What are those edge cases that might cause problems? These are just giving us overall results so far. So when we're actually getting back to this, like what causes us to identify like what is group B in the first place, that's where edge case detection can come in. And that's where we can start to actually find the fields in our data set that are held in common when grouped together might be contributing to model failure. So just to kind of give a little bit of like background insight, some like real world examples of this, of like models failing in the wild, where they might have like succeeded among training data, for example, or they might have succeeded among test data, for example, would be this example where let's say you have uh, an automotive self-driving application. The model is trained on what should be a variety of conditions. The car will attempt to make adjustments if it encounters potholes. And we have a situation where the car is suddenly detecting potholes that aren't actually there. So it's like detecting phantom potholes in the road. Well, it turns out a cause of that could be something like there are trees in the road casting shadows that the model wasn't trained on and therefore didn't expect. Like trees in the road casting shadows was not a common condition that the model anticipated. Another example is imagine you have folks in a grocery store and we have like security cameras that are trying to detect whether someone might be a shoplifter. And there's suddenly a ton of false positives. It's like constantly flagging for shoplifters when there aren't shoplifters. These people are innocent customers. Well, maybe it wasn't trained on people wearing lots of coats in winter. So it thinks that people wearing coats are like suspicious or they're like filling their clothes up with goods. So how can we analyze A, whether this data exists in our training data, or B, if it does exist, when we're actually evaluating the models against test data, if those are the classes in which the model fails? So going back to the model evaluation metrics I showed earlier, let me actually flip to a different data set for a moment. So this is the Berkeley Deep Drive data set, and it's a self-driving data set, and it has a whole host of classification fields as well as object detections and polylines that are part of its annotations. So we have a variety of weather conditions, a variety of scenes from urban to highway to gas stations. Um, we have a variety of uh, bounding boxes against different classes that we can apply, and we also have some model predictions as well. So we have our ground truth, we have model predictions, and we have a whole bunch of different effectively scenarios that we can represent. So if I go to that same model evaluation pane from earlier, I can go into, say, one of these evaluations. Give it a moment to load. And we can see already that it's not very good, like overall. It depends what our threshold is, but overall, like our precision isn't great, our recall isn't great, and therefore our F1 score isn't great. Now we can see the overall metrics and we can see class performance, and that maybe gives us a little bit of insight. So for example, our like success rate for different classes like cars, bicycles, people, traffic lights, and so on. We can see some core metrics there. But where we can get some real value, I think, is through splicing out particular conditions that allow us to see, is there anywhere our model catastrophically failed? So if I go to scenario analysis here, what I have set up is in this case, for example, city versus residential scenes. And we can see that, first of all, by total count, we have much more city scenes than residential scenes. What we can also do is we can get the relative distribution of true positives, and false negatives. Here, it doesn't seem too bad, right? It looks like, other than like the total number, we can see that we have like, or I guess I should say the difference isn't too substantial. The model performed pretty badly, but the difference in distribution between city and residential in terms of true positives, false negatives isn't terrible. We can also see the confidence distribution for each, and that gives us a little more information, right? We can see that there's a much larger confidence range among residential than among city streets. And we can also see the total subset distribution. We can decide, are these numbers what we would consider to be a balanced data set? Based off your industry, is the amount of residential samples, objects, scenes versus city based objects, like what we would consider to be balanced in our data set. Let's look at another example. Let's look at weather. This might be a little bit more obvious, where we can see, okay, why might models fail? Well, here again, we have the distribution: clear, overcast, partly cloudy, rainy, snowy. We see the vast majority of scenarios are in clear conditions. We can see kind of the balance of precision, recall, F1 score, intersection over union, mean average precision. What we actually want is we want this little dialogue, this circle to be filled up. So we can see that there's a couple areas that are clearly having issues. And we can see the confidence distribution here as well. And we can start to see kind of a couple lessons. So first of all, as you might expect, the confidence threshold, the confidence distribution for clear conditions is a little tighter than the other conditions. If I go to F1 score here, though, okay, in these conditions, there's some similarities. There's some similarities in terms of metric performance. What about precision? And what about recall? Okay, so they're not too off from each other. But at the same time, the subset distribution might want to give us pause, right? Are we okay with this balance in our data set? And in addition, even if we have these classification labels on our data set for these different conditions, do we know that the ground truth is even correct? So again, lots of layers that we'll need to go through here. The last one I want to show here is, sorry, let me go back here. Bounding box size also can give us some information if this wants to load. There we go. If we look at the scenario data, we can see we created a scenario in which we created subsets where we organized by the size of the bounding box. They were classified as large objects, medium objects, and small objects with respect to uh, the size of the sample. And in doing so, we can see that we have lots and lots of small objects, but very little large objects. And again, if we have an object that like takes up the sample frame, if we don't have a good representation of that in the data set, that can cause issues. One example is in self-driving data sets, a common issue is detecting the ego vehicle, what we call the ego vehicle, and thinking that it is another car or another vehicle on the road. Um, that can be a major issue because like basically the point of view car is now considered like an object, and we might find that the model suddenly wants to think that like the dashboard of the car or the hood of the car is like a separate vehicle, and that could result in interventions by the software in the wild. Um, oops, sorry, give me one moment here. Apologies. All right, sorry about that. Um, so we see this distribution here. How might we start to analyze what it looks like in terms of our overall data set distribution? One way we can do so is by analyzing whether or not the labels and ground truth are what they should be in the first place. Because here's the thing, even if I see like metrics like this, so first of all, we can see that the model actually performs better on large objects and medium objects versus small objects. What these don't tell us are if the model might silently fail because labels are wrong, right? If the model silently fails because the labels are wrong, this whole thing is useless. So how can we do label QA? That's actually a really hard problem because the entire premise of the success of us building models is especially in visual data sets, is ensuring that we have objects properly labeled with appropriate ground truth. In like large language models and in like text-based models, in a lot of ways, you're like kind of training off the inherent text itself, right? But the idea of a vision model is that you're telling the computer, you're telling the model what the thing is in the first place, and you're giving it, that you're telling it, hey, that this is a cat, C-A-T, and the model's identifying patterns that suggest other cats, but you need to have that ground truth correct in the first place. So when we have all of this here, right, if we don't know the labels are correct, we need to identify those issues as well. So that's where better label QA can come in. And that can be a pretty big bottleneck, especially if the labels turn out to be wrong, where you need to put them back through a QA loop. And there's kind of two issues there. Issue number one is how do we know the labels are wrong in the first place? And issue number two is how do we generate labels that are correct quickly and efficiently? Historically, that's been people doing that. But because vision language models have made so much progress, we can start to use those increasingly more often to have at least a first pass of um, generating labels that can then go through a human review loop. So FiftyOne has a feature that we call verified auto labeling. Um, it's called verified because we realize that ultimately there are some labels that will require human review. At the same time, 95 to 90% of labels in like typical conditions, our research has found foundation models do a pretty darn good job on. So Val uses foundation models to automatically generate labels and then add confidence scoring to the ones that require human review. What you can also do is you can, because you're applying a model, you can set the confidence threshold that the model should have in the first place before we even send those labels to human review. This can be performed much more quickly and cheaply than if you just have just humans manually annotate, 100,000 samples. So what does this look like? Well, let's go see. So I'm going to open up actually a subset of BDD. So it's the same data set, it's just a subset of the data here. And I'm going to actually open up this panel called auto labeling. And we already see we have a couple runs here of label fields added via foundation models. But if I wanted to start a new run, I could click this button here, auto label, and start to walk through the application of foundation of labeling of annotating my data through models instead of just through manual annotation. I can choose the entire data set. I can have a particular selectable view. So in FiftyOne, if I were to filter this data set, I could create a new view and I could choose to label just that view, or I can select like individual samples and label those. Next, I can select the model I want to use and then the type of labeling. Is it classification? Is it object detection? Is it segmentation? Um, let's say we're doing object detection. Well, FiftyOne will offer some suggested models you can use. Maybe it's a zero-shot model, so an open vocabulary model. If that's the case, we will add the classes ourselves that we'd want to label. If it's a fixed vocabulary model, then we could choose from the classes within that model. So zero-shot models have become pretty darn good as of late. So let's say I choose a zero-shot model, maybe YOLO World, for example. And again, this is a kind of a broad open vocabulary model. And then I can define the classes of things I want to label. So maybe person, truck, sign, car, or those might be too vague. It might be stop sign, pickup truck, um, uh, pedestrians and crosswalks, something like that. Regardless of what I put here, I can then add the name of the field that this would be added, that this would become in my data set. So maybe YOLO W auto labels. And then most importantly is this minimum confidence threshold. So again, you're basically saying, when I run this model, what is the minimum confidence that I'll accept for a label? You might think to choose something very high. We've actually found that a lowish to medium-ish confidence threshold for kind of state-of-the-art models is actually preferred because otherwise, because that maximizes recall. And as I said before, false positives are generally a lot easier to root out than false negatives because those are labels on the data. False negatives are like there are no prediction labels on a false negative, and it can be very difficult to like find out why something was missed as or why, versus a false positive, which at least gives you kind of more evaluation capabilities. So maybe something like 0.35 might be like a minimum confidence level that we would be okay with. And then finally, you could give it a run name, and then any attached GPUs that you have, it'll leverage to perform this background run. And what FiftyOne will do, I'm going to kind of skip ahead here. So let's say like I clicked this auto label button, the process runs here. It'll then create a new field that you can analyze. So whoops, if I pull up auto labels, auto labeling again, here we have a run of YOLO World. And we can see what's isolated in this view here are the applied labels of car, person, truck, and bus. We can see the number of instances, the minimum confidence threshold, or the average confidence threshold rather. And even though I set a minimum confidence threshold in like the initial run, you could actually further refine it here. So maybe I'll say like 35 or 36 is my minimum confidence threshold. And at minimum, I can start to take a visual look at what might have been what might be hits and misses. So that might be too high a threshold. Maybe we could do a bit lower. And then maybe we can, again, start to see some additional bounding boxes show up. Now, what's also very nice about using foundation models in this way is it allows us to perform the same model evaluation techniques as we could do on any other model. So, and that's important too, because we can start to see if the model doesn't perform well, are there particular areas in which it might fail and why? So one example of this is analyzing the embedding space. So FiftyOne includes an embedding space, embeddings visualization that you can compute and then visualize. And then you can color by things like label, for example, and so on. And if you see like particular outliers, you could drill in and see, okay, what is it about this section of the space that I might want to do some further analysis on? If it's maybe if I see a cluster of people here, I could analyze this as well. One example I have here that I don't have in this live environment is, real quick, if I skip over in this video super fast, is on one run. So this is actually doing the embeddings computation right now at the object level. It's creating what's called a patch embedding. And you might find that under certain confidence thresholds, you might have an outlier like this in the case of the self-driving data set that might be false positives. So here we see what the model did is it's labeling all of these ego views as a separate car, right? So this is like the hood of the car that the camera is on that's causing reflections, or even the hood itself that the model is labeling as another car. So these might be labels that we might tag for deletion, for example. So when it comes to QAing labels, that's a core aspect to at least knowing that your ground truth is is increasingly more accurate, because if your ground truth is wrong, that will silently degrade your model's performance without showing up in your performance metrics in a way that is easily identifiable or easily interpretable. Okay, one more one more point on embeddings is if I go back to the larger BDD data set, let's go to BDD validation. Here, this is the larger data set, so the embeddings view looks a little bit different. We actually see two very large clusters of data. The reason for this is one is mostly, my guess is either data is nighttime data. The other set is going to be mostly daytime data. But again, if we combine this with the scenario mining that we talked about earlier, we can start to do things like maybe analyze by weather, for example. So we can see here that, whoops, let me clear the selection here. We can see here if there might be any outliers. Like, what is it about this bunch where there might be issues? Well, we see it's tagged as clear, city, street, and night, but the glare from the lights might be causing problems that cause things to be a little bit blurry or something like that. If I were to color by time of day, I might see something similar. So scene or sort of time of day dot label. We can see that again, mostly daytime samples on the right, mostly nighttime samples on the left. But at like the dusk dawn transition, we see some like a bunch of like orange samples tagged as night in like this daytime cluster, right? That might be another way that we can QA, hey, are these labels actually accurate or were these mislabeled? So for example, if I like zoom in on here, heck, if I even just look at this one sample, this is categorized as night. I would argue that this is not night. This looks like daytime to me. And again, just simply through embeddings, you can at least get a qualitative look at what the issues might be. And again, that can go alongside your other label QA as well. And then finally, you can also get a sense of your data set's balance. So it's not only like whether the individual labels in your data set are right or wrong. It's not only what the scenarios are that cause your models to fail, it's also what are you going to do about it? And one of the mechanisms in which you can start to um, improve your models in response is by having better data to train it on. And that comes again, that all is about data set balance. So when it comes to continuous model improvement, there's a couple things we can do. And there's a couple things that FiftyOne makes pretty front and center that you might find helpful. Number one is getting a sense of the quality of your data through common like computed metrics that can give you a sense of the brightness distribution, the blurriness distribution, aspect ratio, near and exact duplicates. It allows you to also kind of organize similar samples as needed. So if I go back here and if I clear my embeddings and I open this data quality panel, we can see a variety of um, metrics that we can compute the quality metrics for. So for example, in this brightness section, we can see this like histogram of peaks, valleys, dips, and long tail. And remember that I can organize this distribution based on other views aside from just the entire data set. So for example, in this view, I see the entire data set and I can like isolate a part of it, like maybe looking at really dark samples from the whole data set. I can also combine this with maybe an embeddings view from earlier. I'm starting to lose out on screen real estate here. Or maybe if I look at this piece, here it looks like a lot of rainy samples. I can get a sense of what they are. Oh, actually, you know what? I think I'm doing the combination wrong here. Um, sorry, I can save a view first of this. Do this real quick. We go back here. Sorry, the order of operations is a little wonky. I do not know why it's not cooperating. For some reason, it's showing the whole view. I know there's a way. I'm sorry. Moving on. Um, same thing with blurriness. Again, I might get a distribution of blurry samples that I can perform analysis on. Finally, let's say that going back here, let's look at our brightness distribution. Let's say this isn't where we want it. Like maybe our long tail isn't long enough. Like we don't have enough representation of very bright environments. We know our model is definitely failing here. How do we augment our data set with more data that might fall under the condition that we want, that we're trying to improve our model performance on? One way would just be flipping through samples of your larger raw data source and manually importing them in, just looking for ones that look bright. That's very manual. That's extremely difficult. That's probably uh, way too time intensive. FiftyOne has integration with common data lakes through a feature called Data Lens. And through that feature, you can take advantage of if your data lake includes features like natural language search through vector embeddings, and you can grab whole pots of samples that meet a certain criteria. So just a little bit under the hood, FiftyOne has this an open source extensibility library called FiftyOne operators, where basically the long and short of it is you import the operator library, you import the software development kit or library of whatever third party like integration you want, in this case, Databricks. And then there's an example of this on the FiftyOne documentation site. The functions are collapsed here for the sake of like the slide. But then you're basically defining how does FiftyOne represent represent a sample from that raw data lake as a FiftyOne sample. And then number two, what are the queryable parameters that I will present in the FiftyOne user interface for users to query that data lake? So what it looks like in practice is something like this. So here I have a connection to Databricks. I currently have, 10,000 samples in my BDD 100K set. So I have 10,000 samples. And in this operator that I've defined for this data source, I've enabled contextual search. And this is taking advantage of something Databricks has where you can take the vector embeddings of your data set and perform natural language search on it. So I might say, bright glare conditions. I normally use a different example, but because I was just looking at highly bright samples, I'm kind of doing something off the cuff, and we'll see if this natural language actually provides anything helpful. So I clicked the preview button. It's querying the data lake. So again, this data lake is outside FiftyOne. There's likely many, many, many more raw samples than that I don't have in my current like annotated data set. And here we can see some results. And some of these might be useful. Some might not be as useful. Again, bright is kind of um, um, subjective. Another example might be maybe I want to like make sure there's actually an object in it that might be easier to understand. So I might actually go back and say pedestrians walking in bright conditions. Because maybe we're worried about our model failing at detecting pedestrians. We can see it's kind of hard to tell. I will open this up a little bit. There we go. If you're able to see, we can see definitely there are pedestrians detected here. The conditions are bright. And then I can choose to import either all the samples matching the query parameters or like a certain number of samples that match that condition. So maybe like 50, for example. And then I can, import it in the foreground or like schedule it on a connected cluster. And then this is going to be, then what I can do is go back through the label QA process as well. So I can kind of close the loop and go through that auto label workflow from before and see if I can, improve QA and improve the labels on that data. All right, give me one moment here. Okay. So with that being said, here's kind of a couple key takeaways. Number one is the math of model performance metrics are often very misleading and they can't be fixed just by tweaking model architecture if the issues are in the underlying data. Two, you want to have an end-to-end process of evaluating what your metrics are, what classes those metrics apply to. So not just the overall pooled F1 score, but also subsets of your data's performance. And then number three, you want to have a loop in which you can QA the ground truth of that data to verify it is accurate, fix those labels if needed, and then also identify are there edge cases and outliers in your data that can result in the need for further evaluation, whether it's due to data quality reasons, whether it's due to mislabeled reasons. So you can balance those and then retrain your models ultimately on better data. So with that said, thank you so much for watching. I will now be happy to field any questions that might come up. I saw one came in chat so far. Anyone have any questions that you might want to put in the Q&A? Or any questions to go in chat? All right. Well, a couple of things I'd recommend. The first is, again, if you'd like to do any next steps, the try.51 environment is something that you can explore in. In addition to that, the open source 51 is definitely something that you can download as well if you're more comfortable with like, Python and working with Python libraries and working with like a local web server. Leonard, to your question, partly. So the features that are available in open source that you don't require enterprise for, all the model evaluation stuff I showed, so model evaluation, scenario analysis, that's all in open source. Embeddings are in open source. All of the curation, slicing, dicing, filtering, that's open source. The ones that are in enterprise only is the data lake integration. That's enterprise only. And then the data quality panel that I showed is enterprise only, is enterprise featured as well. Yeah, good question. Any other questions from anyone? All right. Well, thank you again for your attendance. Again, if there's any question folks have, we have a very active Discord. So if you're interested, if you can actually find it where if you go to voxel51.com at the very bottom of the page, there's like a little Discord button here at the bottom right. In addition, I'm Nick. You can email me at nick@voxel51.com if there's any follow-up or any use cases that might be of interest to you. Happy to connect you with the right people or just give you some additional kind of ideas from my end. But I'd say Discord is where you can definitely find a broader community of folks, including us here at Voxel 51, who are heavily active as well. So with that said, thanks so much for your attendance. Enjoy the rest of your Thursday, and we look forward to connecting with you again soon. All right, folks. Thanks again. I'll close things out. Bye-bye.